Kourou, French Guiana, June 4, 1996. $8 billion of European engineering sit on the pad. The countdown reaches zero. The Vulcain main engine ignites. The massive launch vehicle lifts cleanly, holding a perfectly nominal trajectory for the first 37 seconds. At 39 seconds, the engine swung hard over. Aerodynamic forces sheared the boosters away, triggering the automatic self-destruct sequence. Nearly $400 million of hardware, along with 4 scientific satellites destined for Earth's magnetosphere, rained down into the Atlantic Ocean. In less than a minute, a decade of ambition was erased. And as investigators would soon discover, not a single physical mechanism on the rocket actually broke. The European Space Agency convened an official inquiry board, led by French mathematician Jacques-Louis Lions, to find out what happened. The telemetry data presented them with an immediate paradox. No fire in the engine bay, no structural failure in the airframe, and no faulty steering valve. The total destruction of a healthy rocket traced back to a completely different domain, a single unchecked number hidden inside a 10-year-old piece of software. To understand the explosion, we have to look at the onboard computer in the milliseconds before it issued that catastrophic steering command. The SRI, the rocket's inner ear, passes rotation telemetry to the flight computer. At 37 seconds, it shut down, transmitting an error code misinterpreted as an extreme tilt. The computer aggressively pivoted the engine nozzles to correct a spin that wasn't actually happening. The airframe didn't fail under normal aerodynamic loads. The vehicle tore itself apart because its navigation system acted on a mechanical hallucination. But why did the SRI shut down and transmit that fatal code? The answer is buried in the Ada programming language. Inside the software's alignment function was a specific value called variable BH, which stood for horizontal bias. Its job was to help calculate the rocket's horizontal velocity. The software attempted to take a massive 64-bit floating point number and cram it into a restricted 16-bit integer space. The 16-bit integer has a hard mathematical ceiling of 32,767. At 36.7 seconds, variable BH exceeded that limit. The value outgrew its container. Because the programmers had left this specific conversion unprotected by an exception handler, the system defaulted to its standard fallback behavior. It shut the processor down completely in mid-air. To understand why the horizontal velocity grew so large, we have to look back at the code's original home, the older Ariane 4 rocket. The two rockets had entirely different physical profiles. Ariane 5 was more powerful. It accelerated faster and turned harder, generating horizontal velocity values during early flight that simply never existed in Ariane 4's envelope. The designers knew spaceflight was risky, so they included a secondary backup SRI unit, running in parallel, designed to take over instantly if the primary system failed. This animation shows why that safety net failed. Because the backup was running the exact same code, it fed the identical massive number into the identical 16-bit limit, crashing just milliseconds before the primary unit. Duplicating software across two computers does not create true redundancy. It only guarantees two identical, perfectly synchronized failures. When the Lions report was published, it explicitly noted that no individual engineer was at fault. There was no negligence on the floor. During the Ariane 4 era, engineers intentionally removed the safety checks on variable BH to keep the processor's workload under 80%. They had mathematical proofs showing an overflow was physically impossible on that specific rocket. The fatal error occurred years later. The alignment module was copied from the old rocket and pasted into the new Ariane 5 environment, entirely based on its flawless track record, without anyone recalculating those original proofs. The disaster was the result of an organizational assumption that software validated for one physical reality automatically remains safe in another. The aftermath reshaped the industry. The software was corrected, the lost cluster mission was eventually rebuilt, and Ariane 5 went on to become one of the most reliable heavy launchers in history. But for software engineers, the legacy of Flight 501 is the concept of design by contract. Every piece of code is a strict mathematical agreement tied to specific physical conditions. If you change the environment, the thrust, the trajectory, the speed, you silently void the invisible contract that guarantees the code will work. A program is never universally perfect. It is only as safe and only as reliable as the physical assumptions holding it together.